Okay, so let's talk about a paper that pretty much changed the game. Imagine trying to build a library not for a town, but for every single piece of information on the entire internet. That was the absolutely insane challenge Google was facing, and their solution, the one they laid out in this paper, it fundamentally changed how we all think about storing data at a massive scale.
Back in the early 2000s, Google's problem was growing at the speed of the internet itself. I mean, literally. All the traditional storage systems, they were just collapsing under the pressure. We're not talking about just storing documents. They were trying to store a copy of the entire web, a library that was getting bigger every single second. So what they do? They did something kind of crazy. They basically took the existing rulebook for building file systems and they just threw it out the window. They started from scratch and built something completely new, the Google File System, or GFS. And this wasn't just a small upgrade, it was a total revolution. It redefined the rules of data storage for this new internet age.
All right, so let's really dig in and understand the sheer size of the challenge Google was up against. This was not your average server room we're talking about here.
So you gotta picture this. Their world was made up of thousands of cheap, off-the-shelf computers that were frankly unreliable. And these machines were dealing with absolutely enormous files. The most common thing they were doing wasn't editing a small file, it was having hundreds of machines all dumping data into the same place at the same time, and then having thousands of machines read it all back. This just wasn't how things were done, and it needed a completely new way of thinking.
So instead of trying to fight this new reality, the designers of GFS just leaned into it. They embraced it, and they created a whole new philosophy built on a few really core ideas. The first rule, and this is a big one, is that you have to expect failure. I mean, when you're running thousands of cheap computers, something is always broken. A hard drive is going to die, a network connection will fail, something will overheat. GFS was designed from the ground up to treat failure not as an emergency, but as a totally normal, constant state of being. It had to recover all by itself, automatically, with no one having to run in and fix it. Second, the files were just huge. We're not talking about megabytes like a Word doc or a photo. The standard file was measured in gigabytes, or even terabytes. So to handle these giants efficiently, GFS had to rethink a really fundamental piece of file systems, the block size, and make it way, way bigger to match the huge files. And for what Google was doing, the most common thing wasn't changing data that was already there. It was adding new data to the very end of a file. Just think of it like a logbook, right? You're always just adding new entries at the bottom. GFS was built to make that one specific action, appending, incredibly fast and super efficient. So, with this new set of rules, what did the actual blueprint for GFS look like? Well, it's surprisingly simple and really elegant.
The real genius of the architecture is how simple it is. Let's stick with that library analogy. You've got one master server. That's the librarian. It knows where every single book is, but it doesn't actually hold the books. Then you have this whole army of chunk servers. Those are the bookshelves, and they store all the actual data. And finally, you have the client, which is you, the reader, who wants to get a book. And here is the absolute key to the whole thing. The master, it acts like a traffic cop. The client comes and asks, hey, where's the file I need? The master says, it's over on that shelf, and gives it the location. But then, and this is crucial, the master gets out of the way. All the heavy lifting, all the actual data transfer, happens directly between the client and the chunk server. This design is what prevents the master from becoming a massive bottleneck. So, how did this really clean, elegant architecture actually translate into incredible performance? Well, it all came down to a few brilliant design choices. First off, GFS takes those gigantic, terabyte-sized files and it chops them up into these big, fixed-sized pieces called chunks. And when I say big, I'm not kidding. A single GFS chunk is 64 megabytes. For perspective, that's thousands of times larger than a standard block in a normal file system. It's huge.
And this right here shows you why that huge chunk size is so brilliant. In a traditional system with tiny blocks, the client is constantly pestering the master. Okay, where's the next little piece? And the next one after that. It's just constant chatter. But with GFS's huge chunks, the client asks the master once, gets the location of a massive 64 megabyte piece of data, and then it can just stream that entire thing directly from the chunk server without bothering the master again. It cuts down the overhead by a massive amount.
GFS also had this other special move called an atomic record append. Remember that logbook? Imagine hundreds of computers all trying to write a new entry into that same logbook at the exact same time. This feature makes sure that every single entry gets written completely and perfectly without getting all mixed up and garbled with the others. It was the secret sauce for these giant data pipelines where lots of machines are creating data and lots of other machines are reading it. All right, now for what is maybe the most critical part of the entire design. How does a system like GFS deal with the fact that its parts are failing all the time?
The heart of its resilience is actually pretty simple. Just radical redundancy. GFS never ever stores your data just once. By default, every single one of those 64 megabyte chunks is stored at least 3 separate times on 3 different machines. And it doesn't just toss these copies anywhere. It's smart about it. It strategically spreads them not just across different machines, but also across different physical server racks. Why? Well, what if an entire rack loses power or its network switch dies? No problem. Your data is still safe and sound on replicas in other racks. It's brilliant. The system is also smart enough to know if one of those copies is out of date. See, every chunk has a version number. So if a machine goes offline for a while and misses an update, when it comes back, the master server sees its old version number and knows, hey, that copy's stale. It won't send any clients there until that replica has been updated with the latest data. So when you put all of this together, what was the real impact of this completely new way of thinking about files? Well, you don't have to take my word for it. The designers themselves summed it up perfectly. GFS wasn't just some side project. It became the fundamental storage platform for pretty much everything at Google. We're talking search indexing, the systems that would eventually become Gmail, YouTube, you name it. And the ideas behind GFS, well, they didn't just stay inside Google. They became the bedrock for the entire big data revolution. Its main principles, design for failure, optimize for your actual workload, these directly inspired huge open source projects like Hadoop. GFS was really the essential foundation for other huge Google breakthroughs like MapReduce and Bigtable. And that kind of leaves us with a final thought, right? The principles behind GFS solved a massive web-scale problem 2 decades ago by rewriting the rules for their reality. Today, as we face this new explosion of data needed for training huge AI models, you have to wonder what new assumptions are going to be challenged, and what new rules are we going to have to write for the data challenges of tomorrow?